Hello everyone, my name is Ujin Kim and I'm from the IDES lab at Seoul National University. Today I'd like to introduce a paper titled Artificial Hivemind. This work was presented at New Lips 2025, where it received the Best Paper Award in the DB track. The core idea of this paper is a phenomenon they call artificial hivemind. It refers to the tendency of large language models to produce highly similar responses, even when they are asked open-ended questions that naturally admit many different answers. In other words, although modern LLMs are capable of generating diverse outputs in principle, in practice, they often converge to the same ideas, the same structures, and even the same phrases. This talk explores where this homogeneity comes from, how widespread it is across models, and why it matters for creativity, diversity, and alignment in real-world language model usage. Here is the structure of the talk. I'll begin by briefly discussing why creativity and diversity matter in language models, and how these concepts have traditionally been understood and evaluated in real world. Next, I'll introduce the Infinity Chat, a dataset of real-world open-ended queries designed to study diversity at scale, in settings that closely reflect actual user interactions. Using this dataset, the paper presents two key empirical findings. The first is intramodal repetition, where a single language model repeatedly generates very similar answers to the same prompt. The second is intermodal homogeneity, where different models, even from different families, converge to highly similar responses. Finally, the paper connects these findings to distributional evaluation, showing that current model-based judgments often fail to capture the diversity of human preferences in open-ended scenarios. And in this section, I'll briefly introduce the basic notion of creativity and how modern LLMs deal with them. Creativity has long been regarded as a defining hallmark of human intelligence. Historically, machines were seen as fundamentally incapable of creativity. Ada Lovelace argued that machines can only do what we explicitly instruct them to do. They cannot originate anything new. Fast forward to today, and we hear our most opposite claim that generative AI is perhaps the most powerful creative tool ever built. So, we are faced with a deep tension. Are modern language models genuinely creative agents, or are they simply very sophisticated pattern imitators? Before measuring the creativity, we first need to define what we mean by it. A widely accepted working definition decomposes creativity into two core components, novelty and value. Novelty refers to originality, producing something that is not merely a repetition of existing patterns. A value refers to usefulness or meaningfulness. The output should actually matter to humans. Some definitions further include dimensions such as surprise or intentionality, but these aspects are even harder to operationalize computationally. What's important here is that creativity is not a single scalar property. It is multidimensional, highly context-dependent, and especially difficult to measure for open-ended language generation. The notion of creativity is also related to the distinction between divergent thinking and convergent evaluation. Divergent thinking refers to the ability to generate many different, plausible ideas or solutions from the same prompt. Convergent evaluation, in contrast, refers to the process of selecting or scoring responses according to the shared criterion of quality or correctness. In current large language models, especially during instruction tuning or reinforcement-based alignment, training typically treats the ground truth as a single preferred answer. As a result, models are strongly optimized for convergent evaluation, while divergent thinking is often underemphasized. This creates a tension. Models may appear fluent and high quality, yet still lack genuine diversity in their responses. Because creativity is difficult to define precisely, computational evaluations typically rely on proxy metrics. Common proxies include fluency or quality, originality or novelty, and diversity across outputs. These metrics are easier to quantify, but they only approximate different aspects of creativity. Traditionally, creativity has often been measured using psychometric style tests. For example, models may be asked to generate multiple uses for a given object or to produce many alternative ideas from the same prompt. More recently, many works have adopted LM as a judge frameworks. In this setting, Another language model is used to score generated outputs along these proxy dimensions, such as quality, novelty, or overall creativity. Existing benchmarks evaluate creativity in specific domains. For example, creative writing benchmarks focus on storytelling. Other benchmarks evaluate scientific idea generation, code generation, or even randomness. While these are valuable, the settings are highly constrained and often artificial. They do not reflect how people actually interact with language models in daily life. In practice, users ask vague, underspecified, open-ended questions, the questions that admit many equally reasonable answers. This gap motivates the need for a more realistic evaluation setting. Diversity has also emerged as a central issue in alignment research. Human preferences are inherently pluralistic. Different people value different answers, styles, and perspectives. So, the pluralistic alignment argues that models should preserve this diversity rather than collapsing to a single safe response. From this perspective, diversity is not just about creativity, but about respecting human heterogeneity. If models consistently converge to the same responses even when multiple alternatives are acceptable, that represents a form of misalignment. So, we have covered some backgrounds, and let's continue to the paper itself. Despite the growing interest in diversity and pluralism, evaluations of diversity in real-world settings remain limited. Many benchmarks rely on artificial tasks like random number generation, which do not reflect the real usage of humans. To address this, the paper first introduced the Infinity Chat, a dataset of over 26,000 real-world open-ended queries. Using this dataset, the paper systematically analyzes how language models behave when there is no single correct answer. Based on this analysis, the paper identifies two major findings. First, intramodal repetition, where a single model repeatedly generates highly similar outputs for the same prompt. Second, intermodal homogeneity, where different models, even from different families, converge to similar responses. The visualization on the right illustrates this effect. Although responses appear different on the surface, they cluster tightly in representation space, revealing a shared underlying structure. Together, this phenomena motivate the concept we call artificial hive mind. Let's begin with the dataset and how the authors constructed the infinity chat dataset. First, the paper constructs the dataset called Infinity Chat, with the goal of capturing real user queries that are genuinely open-ended. Rather than relying on synthetic prompts, the authors mine queries from WildChat, a large-scale collection of real ChatGPT interaction logs. From this raw data, the authors apply a series of filtering steps. They restrict the dataset to English, non-toxic queries, generated under GPT-4, and with a reasonable ranks between 15 and 200 tokens. And also, only meaningful information-seeking queries are retained. Something like greetings, causal chit-chat, and model-related inquiries are explicitly removed. In addition, noisy or ambiguous queries are rewritten to improve clarity while preserving the original user intent. Through this process, the authors collect 26,000 open-ended queries and 8,000 closed-ended queries. The resulting dataset closely reflects how people actually interact with language models in real-world settings, making it suitable for studying diversity at scale. This slide shows some representative examples of the open-ended queries included in Infinity Chat. As illustrated here, the dataset covers a wide range of query types, including creative prompts, language manipulation tasks, factual questions, and well-scoped writing requests. For example, some queries ask the model to write short tips for self-development, to name English words under certain constraints, or to paraphrase given sentences. After this filtering step, the authors further categorize the open-ended queries using a hierarchical structure. The queries are iteratively assigned and grouped into 6 high-level categories and 17 subcategories, reflecting different types of open-endedness, such as creative generation, information seeking, decision support, and alternative perspectives. To validate the openness of these queries, the authors then conduct human evaluation with 86 participants. The participants assess both the open-endedness of each prompt and the diversity of possible responses it can admit. The statistics shown here indicate that most prompts require 3 or more plausible answers, and a substantial portion admit more than 10. This result reinforces the motivation of the paper. Real-world prompts actually demand diversity, making them suitable for studying how language models handle open-ended generation. With the infinity chat dataset constructed, the paper then moves on to its main empirical findings. The first finding is intramodal repetition. For the same model, and even when using diversified sampling methods, the model repeatedly produces highly similar outputs in response to the same open-ended prompt. The evaluation setup is as follows. For generation, the authors use 100 open-ended prompts sampled from infinite chat. For each prompt, each model generates 50 responses, using 2 diversified sampling strategies. Specifically, they apply top P sampling with P equals 0.9 and temperature of 1.0, and minimum P sampling with P equals 1.0 and minimum P 0.1 and temperature of 2.0. All generations are allowed to be long with a maximum length of 2048 tokens. For evaluation, the authors compute the average pairwise similarity among the generated responses for each prompt. This similarity is measured using cosine similarity between response embeddings, obtained from the OpenAI text embedding 3 small model. Higher similarity indicates stronger repetition within the model outputs. This figure illustrates the overall similarity distribution of responses for each model. The x-axis corresponds to different models, and the y-axis shows the proportion of response pairs that fall within each similarity range. All results shown here are based on the top P sampling setting. As can be seen from the figure, for most models, a large majority of responses fall into the high similarity range above 0.8. In many cases, more than 80% of the response pairs lie in this region. This indicates that even with relatively high temperature and stochastic sampling, a single model tends to generate responses that are semantically very similar to each other. In other words, diversified decoding alone does not prevent strong repetition within the same model's outputs. Then, this figure shows the same analysis under minimum P sampling, which is often considered a more aggressive strategy for encouraging diversity compared to top P sampling. Minimum P adjusts the sampling distribution by filtering tokens based on the confidence, allowing higher temperature while removing extremely low probability tokens. As expected, the proportion of response pairs in the highest similarity range is reduced compared to the top P setting. However, even under this more diversified decoding strategy, the average pairwise similarity among responses to the same prompt still typically exceeds 0.8. This also indicates that although minimum P sampling slightly alleviates repetition, the same model still produces largely similar outputs, reinforcing the persistence of intramodal repetition. Following the analysis of intermodal repetition, the paper then moves to its second main finding, the intermodal homogeneity. Here, the focus shifts from variation within a single model to similarities across different models. Specifically, the analysis examines whether models from different families, sizes, and training setups still converge to similar outputs when responding to the same open-ended prompts. Using the same generation and evaluation protocol as in the previous section, the paper then analyzes intermodal homogeneity. In this setting, responses generated by different models are compared for the same open-ended prompts. The paper reports 3 main findings. First, models of different sizes and from different families still produce highly repetitive outputs. Second, phrase-level overlaps are prevalent across models, indicating shared expression patterns. Third, despite the surface-level variation, models tend to convey the same core ideas in their responses. Together, these results suggest that homogeneity is not limited to individual models, but is a broader phenomenon across the language model ecosystem. First, The paper analyzes the intermodal homogeneity by measuring similarity between responses generated by different models for the same set of open-ended prompts. The figure on the right shows the average pairwise embedding similarity across the models, using the same embedding-based metric as in the intramodal analysis. Here, each axis corresponds to a different model, and each cell represents the similarity between responses produced by two models for the same input set. As shown in the heat map, the average similarity consistently exceeds 70% and often reaches around 80%, even across different model families and sizes. This indicates that, despite architecture and training differences, different language models tend to generate highly similar responses when faced with the same open-ended queries. In addition to high embedding similarity, the authors observed that direct phrase overlap is also prevalent across different models. This example shown here compares responses generated by Llama and GPT for the same prompt, generating a short description of an iPhone case collection. As highlighted in the figure, a large portion of the text overlaps at the phrase level, including expressions such as sleek, slim-fitted case collection, bold, eye-catching designs, and make a statement. This slide shows another example of phrase overlap across different models, using a prompt that asks for a short motto about success, wealth, and self-help. Here, the responses generated by Llama and QN are almost identical, both in wording and the structure. As highlighted, the models produce the exact same core phrase, such as empower your journey, unlock success, build walls, transform yourself. This example further illustrates that intermodal homogeneity can be so strong that different models sometimes generate nearly identical outputs. Furthermore, beyond surface-level phrasing, the authors find that different models often converge on the same core ideas. This slide shows an example where models are prompted to write a metaphor involving the time. Across a diverse set of models, most generations fall into a small number of recurring conceptual patterns. In particular, two dominant metaphors repeatedly appear. First, time as a river, and second, time as a weaver. As illustrated in the examples, models independently describe time as something that flows, carries moments away, or continuously weaves experiences into life's fabric. This pattern emerges consistently across model families and sizes. This demonstrates that intermodal homogeneity extends beyond wording, reflecting a strong convergence at the level of underlying conceptual representations. These slides present concrete examples illustrating how intermodal homogeneity appears at the level of core ideas. First, consider the prompt asking for a metaphor involving time. Even when the prompt is slightly paraphrased, different models repeatedly generate the same underlying metaphor, most commonly describing time as a river. As shown here, both Llama and Gemma independently produced responses centered around flowing rivers, currents, and inevitability, despite differences in wording. A similar pattern appears in the second example, which asks models to write about how the internet has shaped society. Across multiple models and prompt variants, responses consistently begin with phrases like, "The internet has profoundly shaped society," and emphasize nearly identical themes, such as communication, access to information, and social transformation. These examples demonstrate that intermodal homogeneity is robust to paraphrasing and persists across tasks, suggesting that models tend to converge on the same dominant conceptual framing rather than exploring diverse perspectives. This slide provides a geometric view of intermodal homogeneity using embedding space visualizations. Each point corresponds to a model's response, projected onto the first two principal components of the embedding space. On the left, the plot shows responses to the prompt, "Write a metaphor involving time." Despite coming from different models, many responses cluster tightly together, reflecting the shared conceptual structures. On the right, a similar pattern appears for the prompt, "Name one meaning of life." Again, responses from different models collapse into a narrow region in the embedding space, indicating limited conceptual diversity. These visualizations further support the paper's findings that different models tend to occupy similar regions of semantic space, reinforcing the presence of strong intermodal homogeneity. So further, the paper has examined the construction of the infinity chat dataset and uncovered strong patterns of intramodal repetition and intermodal homogeneity. Building on these findings, the authors then turned their attention to how creativity and diversity are evaluated. In particular, this section focuses on distributional evaluation and investigates where current evaluation practices can adequately capture the diversity of human preferences in open-ended generation. Human preferences and values are inherently distributional, rather than single-point levels. For many open-ended or subjective questions, different people may reasonably favor different answers, each with varying degrees of support. However, most existing alignment and evaluation objectives implicitly assume a single correct or preferred response, forcing models to collapse this natural pluralism. As a result, responses that humans may view as largely equivalent can be artificially separated by the model or the evaluator. Recently, several studies have begun to address this issue by explicitly modeling distributional preferences, incorporating them into alignment objectives, reward design, and even evaluation procedures, such as in RA-chip-style pipelines. This paper then analyzes this idea using the infinity chat dataset. The goal is to examine whether scores produced by language models, reward models, and LM judges actually align with human preference distributions rather than single labels. To do this, the authors first construct distributional human annotations, combining absolute query ratings and pairwise preference judgments across a diverse set of open-ended responses. In parallel, they gather scores from language models, reward models, and LM-based judges, including perplexity-based scores, Scholar reward outputs, and rubric-based evaluations. The setup allows them to directly compare how well different model-based judgments reflect the full diversity and pluralism present in human evaluations. This slide summarizes the statistics of the human annotations collected in Infinity Chat. We observe that human evaluations exhibit high entropy, reflecting substantial disagreement across annotators. This is expected for open-ended queries where multiple responses can be equally valid but appealing for different reasons. As shown in these histograms, some query response pairs produce highly concentrated preferences, while others lead to broad multimodal distributions. This highlights that human judgment is inherently distributional, rather than something that can be captured by a single score or label. In this part, the authors compare model-based ratings directly against human scores for open-ended responses. Their analysis focuses on two challenging settings that standard alignment often ignores. First, they look at cases where multiple responses have similar overall quality. Because concurrent alignment pipelines usually assume a single correct or best answer, models tend to struggle when several alternatives are equally good from the human perspective. Second, they examine cases with high annotator disagreement, where human preferences are inherently diverse. Since alignment data is typically collected from high agreement examples, model judgments become noticeably less reliable in these high entropy regions. Overall, the results show that model human alignment weakens precisely when human preferences are most pluralistic. These two plots show the correlation between human judgments and model scores when responses are of similar quality. The top figure corresponds to absolute ratings, and the bottom figure shows pairwise preference rankings. Moving to the right means we are restricting to cases where humans assign increasingly similar quality to different responses. In other words, from a human perspective, these answers are nearly interchangeable. As we can see, model-human correlation consistently drops when as responses become more similar in quality. This suggests that models tend to artificially separate responses that humans consider equally good. The same trend appears in the pairwise setting below, indicating that this limitation is robust across evaluation protocols. This figure shows the results for cases where human raters themselves disagree. As before, the top row corresponds to absolute ratings, and the bottom row to pairwise preference rankings. In this case, moving to the right indicates the higher disagreement among human annotators, that is, cases with greater uncertainty or pluralism in human judgment. We again observe a similar pattern to the previous slide. Human model correlation steadily decreases as disagreement increases. In highly disputed cases, model scores often become weakly correlated or even uncorrelated with human judgments. This suggests that current models struggle most precisely in settings where human preferences are inherently diverse, reinforcing the limitations of point-based alignment objectives. This concludes today's presentation. I have introduced recent findings on intermodal homogeneity and distributional evaluation, highlighting how current alignment and evaluation paradigms struggle with diverse pluralistic human preferences. As language models are increasingly deployed in the open-ended, subjective settings, accounting for preference distributions rather than single-point judgments will become an increasingly important research direction. And I believe this perspective will continue to gain significant attention across the alignment and evaluation communities. Thank you very much for your attention. Please reach me at this email shown on the slide if you have any question.